Starting with the title
Hello
here.
and welcome to the New York City Category Theory Seminar. Tonight we have Raymond Puzio talking about gentle introduction to something geometry.
Synthetic differential geometry.
Differential geometry. Anyways, take it away.
Yes, so, all right, now we can rotate.
Rotate.
So, yeah, so I just wanted to talk about, synthetic differential geometry. So it's basically a certain approach to differential geometry, making use of category theory. And fundamental idea there is how to make, one way of introducing it, the fundamental idea is how to make use of the idea of an infinitesimal. So you probably all know that, before about 1800, when people did differential geometry or calculus, usually the way they did it was by using an infinitesimal. So the idea is what is an infinitesimal? Well, it's some kind of quantity, which is like a number, but it's a infinitely small number. So for example, we something like, imagine there existed a real number that is, say, smaller, bigger than 0, but smaller than any rational number, for example. And of course, using that, if you allow yourself to, the assumption that such a thing exists, then it's very easy to do calculus with. Then you can use it to do calculus. For example, how do we define derivative? Well, you would say, could just say I take one of my infinitesimal quantities and I just take the difference, take the difference and there I go. No limit required, that's what I call derivative. And then of course, given this definition, for example, it's things like the, chain rule are obvious, right? You just cancel out, you get the chain rule, etc. And you can also think of it geometrically. So for example, if I had a curve here, say some curve, then I want to, obviously given 2 points, I can connect them, I get a line, secant line. And now, but if I have infinitesimal, I could imagine, well, suppose I pick the 1 point infinitesimally close to the other one, connect that, well, what am I get? I'll get a tangent to the curve. So it's, if such things exist, they're very convenient, they're intuitive, but the problem is, of course, as you know, that when, in the 1800s, when people finally came out with logic, like Dedekind and Cantor came out with logically precise definitions of real numbers, and then, they didn't contain infinitesimals. And then in order to actually justify, results, Weierstrass had to take limits. So instead of just saying I have an infinitesimal, I divide by it, I take a non-infinitesimal epsilon, then I take the limit as that thing goes to 0. So the limit is, yes, it'll get arbitrarily small, but at no point does it actually become infinitesimally small because there's no such thing as an infinitesimal real number. Now, so that was how things, stood in the 1800s. But surprising thing was that about 100 years later, some people find out, well, actually, you can make sense of infinitesimals in a perfectly well-defined logical way. And so I'll just start with a few minutes about how that happened. So first, so there were two different things. So first I'll mention, one was what we call non-standard analysis. That was by Abraham Robinson. And I brought a small introductory book on that. You can look at it. That's just a nice half-popular account of how that goes. But the basic idea there was he was studying model theory. And in particular, he noticed that with some theories, you could have a theory where some logical system where if you were using second-order logic, it would specify a unique model. But if you went to first-order logic, you would get non-unique models. And in fact, an example of that would be, Peano's axioms for natural numbers. And so basically, without going too far into this, the idea is that one important principle you have in your axioms, right, is induction. That tells me if I have a set, and if that set, contains 0, it contains a successor, and nothing else, well, it's the natural, that must be the natural numbers. But then what do you mean by knowing that that's all it contains? Well, if you're in the second order logic, I can quantify over different sets. And so I can say, well, pick the smallest one. That's the natural numbers. But if I'm doing first order logic and I can't quantify over, sets or predicates, I don't get to do that. And then I can have a loophole that I could actually have something that obeys the piano axioms but contains, in addition to the usual number, 0, 1, 2, 3, an infinitely big natural number. It would satisfy the axioms unless I can actually quantify over sets to see that's the smallest one. There's no way of excluding that. So that contains, okay, so now also I've got a thing that's consistent logically as first order logic, but it gives me an infinitely big natural number. So now let's say I want to make rational numbers. Well, if I divide 1 over an infinitely big number, I got an infinitesimal. So there we go. If you use first order logic, you can actually get, a logically consistent version of infinitesimals. And then you can develop analysis using those. And in fact, you can prove all the usual theorems of analysis, using this approach. And for example, this book outlines some of that. And a little later in the talk, I'll actually give a definition of the
is that infinitely large number unique?
No. I mean, well, I guess unique. I guess to say it's unique, you have to say in what, how would you specify it uniquely out of all elements?
So, for example, if you take one such system that contains at least one infinitely large element, right? Is that element the only one that's infinitely large, or can we have more?
Well, of course not, because I can take that element plus 1, element plus 2, right? Because natural numbers, if they're natural number, a successor. So at the very least, if I have an infinite large number n, I'm going to have certainly n plus 1, n plus 2, and I may have others. And there's different, non-standard models, some of which contain more infinitesimals, some which contain fewer.
Okay.
So the non-standard models are not all elementary equivalent to each other?
Yeah, it's just that they're different ones, certainly. I'm not sure the technical phrase of elementary equivalence, but certainly you can, for example, get different ones, yeah.
So then is there like a most efficient model of the natural numbers with an infinite element?
Well, I'm going to get to something like that when I show you the non-standard reals.
Because I would imagine there would be some like...
So there is sort of one, yes. Okay. Yeah, basically we use an ultra filter and do it, and I will say a few words about how you explicitly can get one. For now, I just wanted to make it aware of how just the general, now I just want to go over the general idea. And then I will put the detail in a little bit. So I'll save that. Now, so that was one thing. But then in a totally different direction.
Come up with that?
Who?
When did he come up with that?
That was I guess maybe 40s, 50s, 60s, somewhere around. Mid-50s. Somewhere around there, yeah. Somewhere in the mid-20th century, all this happened. So Robinson was doing model theory. And at the same time, now sorry?
Oh, but then if there can be possibly many infinitely large elements, how do we know which one to pick to define
so basically, I'll give one answer to that there's a meta theorem that tells you when it doesn't matter. So basically, you can show that, if you take any statement about real numbers, say, or natural numbers, depending which way you're doing, let's say natural numbers. You take any statement that you can formulate in first order logic and does not explicitly mention infinite elements. Then, if you can prove that statement using your infinite elements, there will be a proof that doesn't involve them. So you see the strategies, let's say I want to prove something like, let's say I'm using non-standard real numbers now, not just natural numbers. I want to prove something like the chain rule. So I can do my proof using an infinitesimal. But then the point is, but I can state the result. The chain rule can be stated as as a statement in first order logic, and it doesn't mention infinitesimals at all. Hence, I know that if I've proven it using infinitesimals, I've proven a correct statement. So the answer to your question is, it then becomes a matter of convenience. You pick whichever one makes it easier for you to do your calculation. And you know in the end, if you're proving that you'll have a result that's valid.
Okay.
So that would be the, yeah, so that's the strategy here.
Okay.
All right, so that was...
Kock?
What?
What's that theorem called?
Well, I don't know. I mean, you could look it up in here. They have something like, they talk about transfer principles and other principles like that, which...
Categoricity?
Well, categoricity just means, I think, that there's a unique model, which isn't the case here. But if you look in this book, you'll find it. I wouldn't remember off the top of my head. But they have, yeah, they have three basic principles. I remember they call IS and T principles, and somewhere in there is the statement I'm making. And like you said, anyone who wants to, you know, delve more into that, I will recommend this book, Non-Standard Analysis by Alan Robert, as an introduction would cover that. So around the same time, we get the algebraic geometers and category theory. So remember, this was, you know, at the same time Robinson was around doing model theory. Well, Grothendieck computers started to do, you know, categorified version of algebraic geometry. And in algebraic geometry, even, you know, going back before then, let's say into the 19th century, people had a notion of infinitely nearby points and things. And since you're working with polynomials, basically you can make that well defined. And so in particular, so moving, for example, you've probably maybe heard of Zariski's definition of a tangent space, or a tangent vector, where by just using, where you can geometrically define, where you can define that purely algebraically without any limits involved. And you can take that definition and, you know, view it in a way that, you know, interpret in a way that involves infinitesimals. And I'll show you that in a moment. So the point is that what happened was that, you know, Kock and Lawvere then, so let's say then, since we get, let me just write down, so what they noticed is that if you take some of these constructions from algebraic geometry, like this Zariski tangent space or the neighborhoods of the diagonal, which is basically an elaboration of that, the interesting thing is they don't just work for polynomials, you can actually get them to work for smooth functions. So that means that you take these algebraic techniques, which, you know, you could interpret as making sense of infinitesimals, and they will actually work not just for polynomial functions or algebraic functions, but actually for all smooth functions. And that is basically the idea of synthetic differential geometry, and now I will start, you know, and I'll show how that goes. So first question is, you know, first thing I was going to do is to say, well, you know, as we said, first problem was that when you define real number system, you know, formally using dedicated cuts or whatnot, you don't get any infinitesimals. So where are you going to get your infinitesimals from? Well, the answer is quite simple. We'll put them in by hand. So oh, sorry about that. So what we can do is we can say, take our good old real number system that has no infinitesimals, and let me just adjoin an element epsilon to it. So I've got, you know, so now I have the ring of polynomials, say, in this one generator epsilon. And now, how do I make an infinitesimal? Well, I can simply put an ordering on it. Suppose I just demand that for any so let me just require that for any rational number q, or yeah, or let's say plus. Oh no, I don't want it. Sorry, I want it to be a. Yes, strictly bigger than 0 and less than that rational number. And then you just check, using definition, check that this is a self-consistent and gives you a well-defined ordering on things. So I've got a ring with an infinitesimal. And I can do variants of this procedure. For example, for some applications, and one thing it says we don't really, we may only work with the first few powers of epsilon. So we could just, for example, say impose the relation that epsilon to some power is 0. In particular, I'll work for a lot with the simplest instance of that, which is just say that I only have the first power, the second and higher power is 0, and this is something that sometimes, especially in computer programming science, gets known as the dual numbers. So that's just real numbers where I add a generator that squares to 0.
But this is also an ordered field, right?
Yes. That's right. And in fact, here this condition will automatically follow without even having to be imposed. The only way to order is to make epsilon infinitesimal here. If
You're saying epsilon is the same as the dual number epsilon?
Well,
I did not know that.
Well, in the dual numbers, my epsilon squares to 0.
Okay.
Here, I have all powers of epsilon.
Yeah.
Here, I simplified, I added, yeah.
Is it like the same, like the epsilon in dual numbers is also an infinitesimal?
Yes, absolutely. Absolutely, that's the whole idea, yes.
Okay.
Maybe a point of clarification is that,
Yeah.
like, especially in algebraic geometry, we don't really ever consider the order, right? So
Sure.
So you don't. So
Yeah.
usually when you read about the dual numbers, you
That's
don't
right.
hear people say that epsilon is infinitesimal in
Yeah.
that regard
Right.
because it's not an order is never considered. Right?
Okay.
Anyway. That's like, 'cause I'm building up to differential geometry, so sort of the algebraic geometry I'd be looking is a little bit more like real algebraic geometry, which is certainly a lot less common than complex algebraic geometry, which is the way it's usually done. But yes. But in fact, the reason for it is quite simple. You see, if epsilon squares to 0, right? Well, just multiply on both sides by epsilon. And you'll see that, if I compare, let's say, epsilon to 1. Well, I take, let's say I want to compare epsilon to 1, multiply by another epsilon, I'm going to get a 0 and an epsilon.
Okay.
So you can just, just from, in a few minutes, you can convince yourself that the only way to order the thing is to make epsilon consistently. If it's going to have to square to 0, if it was if it wasn't infinitesimal, then you'd get a contradiction by having its square be 0, because the square of something,
Yeah.
So just for that reason, but point is, so you can certainly do it, and you can do many ways. You can, instead of epsilon, I could add an epsilon 1 and epsilon 2, maybe make epsilon 2, even smaller than epsilon 1, etc. So there are many variants on this. There's no problem concocting a ring that has infinitesimals. The hard problem is, though, that in order to do, calculus, I don't just want to have infinitesimals. I want to be able to say, what does it mean to evaluate a function on an infinitesimal? All right, and so that's where, where we have to, so to answer that question, one way of going about it, I would say, is let's just think of how you define the notion of a function. Because we want to now say, I'm going to have functions such as smooth functions which can take infinitesimals as arguments. So how do I go from my usual notion of a function to those? Well, one way I'd like to do is just let's think of the ways you define functions. So one definition people know, is extensional definition. So that just means I define a function by basically giving a table. For each argument, I just tell you what value it has. Now, given that definition, it doesn't immediately tell you how to generalize it to, some other kind of argument. If all I've told you is what f of x is when x is a real number, that doesn't automatically tell me what I should define it to be for something else infinitesimal. But that's not the only way of defining a function. Another way is is the intentional definition. So there, instead of just tabulating values, you tell me intentionally, I have to tell you, well, what is some rule that I use to compute the value of the function from the argument. And so example of that would be, let's say, polynomials, right? Where a polynomial, well, it gives me a certain procedure. You take the input, you multiply it, you add it, and after a certain amount of multiplication additions, out pops the answer. And so, for example, so if I'm working, say, with, if I just restrict myself to polynomials, then I have no problem figuring out what it means to evaluate a polynomial, an argument that, say, happens to be one of these dual numbers. Or for that matter, if the argument happens to be a matrix or a complex number, because I just use the same procedure, but on one of these things instead. And then it's very easy to check that, so let's say if I have a function that is a polynomial of one variable, then I can easily check that, in fact, that, take f of x plus epsilon, I'll get f of x plus epsilon times the derivative of f. So you can, that's easy enough to directly check, but let me just mention for purposes we want a particular way of proving this simple fact. So suppose if I had a function, take any function, any polynomial, well, if I took the polynomial of x plus y, of course I could expand the thing out. And I get a whole bunch of monomials, in x and y. Then let me collect together the ones that don't have, if I collect the ones that don't have any power of y, well, I get f of x back. Then next, I can collect, the powers, the guys that include 1y. So I just regroup the things.
Yeah.
And now,
where it's 0, so.
Well, that's right. So when I put an epsilon in, this will happen. And then why is this the derivative? Well, one easy way to check is, well, just take let's say x was a real number. If you just put in, definite derivative to the limit, you would instantly see that, yes, this thing is indeed the derivative. So it is a derivative, but now the point is we can get it, but the point is we got this thing purely algebraically. All right, so in terms of, so if we're working polynomials, yes, we can, evaluate them on infinitesimal arguments, and we can get the derivative that way. And then, and it's obviously then, with a little bit of elementary checking, you can then just derive all the usual rules of calculus for derivatives and be off to the races. All right, so now the question is, how can we, this is all good, but how, but now let's say my function was not a polynomial. Let's say I want to do it for smooth functions. How can I extend this? Well, one way is say, first of all, we'll broaden our view of a function. So let's start with polynomial. So I could obviously, one way of giving a polynomial, like, I don't know, like this or whatever, well, I can view it two ways. I can either view it as it's a description of a function that turns, given a value x, returns some value, or I could just think of this as a purely algebraic expression. And if I think of it as an algebraic expression, then I know that I can operate on the algebraic expressions. I can add them, I can multiply them, so I get a ring of polynomials. And so I can say, what is a polynomial? Well, it's an element of a ring. And then, okay, so if it's an element of a ring, well, what happened to evaluation? Well, evaluation is that at a particular value x. Well, that's an operation that maps polynomials into values. So let's say if if I'm evaluating the real values, it's going to be, evaluation at some point, let's say 1.8 or whatever, well, what is it? It's going to be a map that sends polynomials to real numbers. Furthermore, it's not just any map, it's going to have to be a ring homomorphism. Because if I evaluate the sum of two polynomials, I get the sum of the things I evaluate, and same with products. And, all right, so, and furthermore, but now there's another nice, but the other nice fact is that evaluation at a point is the only homomorphism from polynomial in X to real numbers. And we can see that, in fact, you can see, it basically follows from this fact. Or in fact, even a simpler version of this with this thing left off. You see, suppose I have some map, mystery map, that's a homomorphism from real numbers from polynomials to real numbers. Well, one polynomial is just the identity polynomial, f of x equals x, right? So I'll take phi of that identity polynomial, that's a real number. Let me just, I'll give that the name, I'll call that number xi. And I'm going to claim that, and now for any other polynomial, I use this fact here. So given an arbitrary polynomial, well, I can, let me write in fact a slightly different way. I can write f of x as f of xi plus x minus xi times this other polynomial. So just this, well, in xi, but okay, fine, that's a constant, right? So I write it that way. That's just the fact I had before from collecting terms. But now, suppose I apply my map phi to it. Well, phi is a homomorphism, right? It's an algebra homomorphism. So if I take phi of f, you see, what am I going to get? Well, I'm going to get the value of this, because this is a constant. So if I apply a constant to it as a homomorphism, it's give me that constant back. All right? But then it's a homomorphism, I'm going to get phi of x minus xi times phi of g. But you see, it's phi of x minus c. Well, that's phi of x minus phi of xi. But by definition, but xi is a constant, so that's phi of x minus xi, which by definition was 0. So phi of f is just f evaluated at xi. Now the point is, I got the value at xi, but all I ever mentioned was that I had a homomorphism into real numbers. So we can extend that to say, well, if I want, suppose I want to evaluate it with a dual number. Well, then just let's consider instead put the target ring to be the dual numbers. So instead of mapping into real numbers, I map into dual numbers. And basically, by that same argument I hear about the epsilon squared to 0, you can check that any such map, you know, so let's call it psi, must be of the form psi is simply of f will equal f at some point plus constant times epsilon times the derivative at that point. By the same argument that I gave earlier. All right, so that's how we can define, how value of a polynomial by only using the algebraic structure. Now here's the interesting. The amazing fact is that we can carry this argument over from polynomials to actually all smooth functions. How come is that? Well, basically because this formula here would hold for smooth functions as well, right? Because if f is a smooth function, I'll write it as an f prime. Well, what is this? This is just the first order Taylor series with remainder. Yes?
What if our smooth function is not analytic?
It doesn't have to be. I'm only doing Taylor series to first order with a remainder.
But there are smooth functions that cannot be approximated by their Taylor series at all.
Well, they can be. No. Analytic means infinite order. The Taylor series converges to infinite order. I'm only truncating the Taylor series here at first order with a remainder. So that I can do for any smooth function. If it
like the remainder might still be smooth, but not.
Yeah, the remainder doesn't have to be analytic. Analytic means that the Taylor series exists to all orders and converges. With smooth, I'm only doing a finite order. I only take a finite number of orders and I have a remainder. Yes?
I think there's a caveat we forgot to mention
Sure.
about doing all this cool stuff.
Yeah.
Which is that we have to be in a non-classical logic, right? If I recall. Because if you have excluded middle, this doesn't work, and I think you should mention that.
Well, so the excluded, yeah, well, so there's 2 points. See, I'm taking that's sort of the internal versus the external point. Because I'm thinking it's externally, where I say I have my ring D with infinitesimals. So from the outside, this is certainly correct. Now, if I try to describe it internally, where I imagine the infinitesimal as sitting inside my real number system, then yes, I would have to restrict the logic I could use.
I don't follow it, that's okay.
Yeah. No, because here I'm just describing externally. Because well, I'm saying there's external and internal. Internal description is I say I have polynomials, I construct this other ring, which is not the real numbers, with my infinitesimals.
I just think that there's certain things that would collapse still if you use classical reasoning about that ring.
Well, no, if we have classical reasoning about the ring, that's fine. You just have to be consistent, and because you would never put the infinitesimals into the real number system, right? They live in a totally different ring, which classically would look like classical real numbers to which I've adjoined an epsilon.
Okay, I see what you mean. So your syntactic and semantic worlds are kept so separate here.
Exactly.
Where the contradictions arise when they bleed into each other.
That's right.
Yeah.
That's right. So you're right. There's an equivalent description of this where I would, where I would allow the infinitesimal euro, but then the price I pay is I have to restrict my logic to avoid contradictions. Yes.
So this formula, it suggests that as long as you're only interested in functions up to their first derivative, you don't really need to consider smooth functions. In other words, you can consider a larger class of functions.
Well, you could do that, sure.
Yeah, with less derivatives.
Well, yeah, I mean, obviously I could just do C2 functions, for instance. That's right. But now if I wanted to, ultimately say, well, I want, if I want to go beyond just going to first order, then I might want smooth. I mentioned smooth but you're absolutely right. If I only want it first, I could just do C2 functions and get away with that.
Well, do you even need that? You just need to see one function.
Well, okay, but there is a subtlety, actually.
Oh, okay.
You see, remember, if this is only Cn, the remainder term is going to be Cn minus 1.
Okay.
But why do we even care about regularity of the remainder at all?
Well, because if I want this argument to work, I want to say that, I have a map, all these things live in my algebra of functions. So if I have a smooth function, I want to be able to use an argument where I say I have a mapping of function of smooth functions to smooth functions. I better make sure everything is a smooth function or that argument won't work.
Oh, okay. So C2 is sort of the minimum.
Yeah, that's right. Now C2, be careful, because then this would be, C1. The convenient thing about infinity is infinity minus 1 is infinity. Or never mind what infinity is. This is not even Robinson's thing. This is purely. But, if this has derivatives of all orders, smooth, then so will the remainder.
Oh wait, so that's saying that what I'm saying is just wrong. You can't restrict to a larger class of functions. You have to take also.
Well, you'd have to do more work.
Okay.
Right, where you'd probably have to keep around the C2 ring and the C1 for the remainders to live in.
Oh, I see.
But I never tried to differentiate the remainder. So you could do it that way if you wanted to, just, it would be consistent.
But here I have one question. So by definition, we know that if both x and y are real numbers, then f is smooth, or at least f
Yes.
is C2,
Right.
then this formula is correct. We can verify it. For polynomials, we could replace.
Sure.
If for polynomials, you could easily say that generalize x and y both into the dual numbers.
Yeah.
And then the multiplication rule still gives us a
That's right.
result. We can also verify that.
That's right.
But now, if f is a smooth function, and we let both x and y live in dual numbers, now I don't see how can we do
So what I have to do then is, what I want to generalize is the version of it where I view evaluation as this algebra map, you see. So what I want to do is ask, let's say I take, so now what I'm going to do is, okay, now I can use this board. See, the point is, what I was saying is, in polynomials, given this, as you said, it was perfectly straightforward to see how I would evaluate a polynomial on a dual number. Now, with a real number, with smooth function problems, well, I don't know how to a priori do that. However, for polynomials, I noticed that evaluating at a dual number was equivalent to finding a homomorphism from the ring of polynomials to the ring of dual numbers. So now what I'm going to do is propose that we look at what is a homomorphism from C infinity to dual numbers.
Called an R derivation, right? It has a certain, like the module of all such derivations.
Yeah, of course.
Certain
Yeah, it will.
property that.
Yeah, of course. Yeah, it will be a derivation, sure, of course.
Maybe an idea to keep an eye on the time.
Sorry, okay, well,
You want to move forward.
yes, I will. Yeah, well, please, once I get the basics, everything will fall quickly. I just want to get this right, because then everything else follows from it. So, point is basically by using the same argument. See, the point is, in this argument, all I used was the fact that I had such an identity. I have such an identity in real analysis. It's called the Taylor series of remainder. And so the point is that that allows me algebraically to show that any such map must be of the form, C of f equals f at some real point plus some epsilon times the derivative. So basically shows that, if I divide the dual number, that makes this thing into a homomorphism. All right, so then that's the basic point. So now what I'm going to do next is just say a bit about, so if you grasp that, that's the basic, the reason I spent time on it, and I'm mindful of time, is that this is the basic principle. Once you grasp this, that we've, defined the notion of how do I evaluate a smooth function at an infinitesimal argument in terms of this map of the rings as a homomorphism from the smooth function ring into it. That's basically the whole secret or sauce that makes synthetic differential geometry work.
It's like I would take this formula, but I still think that the fact that we need to. The fact that if you want to prove this formula, we need to use
that's right. Well, point is, I'm not trying to prove the formula. I'm just saying if you assume that formula, you assume that formula with whatever proof it has, then you can, that gives you that's an algebraic fact.
Okay.
That's what I'm saying.
So we have to assume that.
I'm taking it as an assumption, yes.
Okay.
And in fact, in synthetic geometry, Kock likes to call that formula the Fermat formula, and Lawvere thinks of it as an instance of what he calls coincidence of opposites. But basically, there it's taken as, it's taken as an axiom. So you take this formula as an axiom, but a nice thing is that even though to prove the formula, I may have to do some analysis. In the end, it's an algebraic statement about the algebra of functions.
So can we alter that axiom and still get some system that's valid, or is
maybe
like
so, but I'm not going to worry about that now.
Okay.
Probably could, but for now I'm just going to stick with this one because it works.
Okay.
So given that, now the point is, so what can we do? Well, first of all, like I said, using this setup, one can, as is done in the first chapter of this book by Bell, you can basically develop all of, your usual elementary calculus, chain rules, everything from that. But we can now now I'm going to go further into realm of geometry. So basically, how can we use this to do so? In algebraic geometry, well, instead of polynomials, we would study, varieties, algebraic varieties, so these surfaces on which it's done. So then differential geometry, well, the analog, that would be a manifold or some such space, and we'll generalize space. So how do we do it? Well, as you know, the basic idea from algebraic geometry is, that I specify my variety by giving you the ring of all real functions on it. So I have a space, and then what I'm going to do is consider an algebra, right, of functions from that space to the real numbers. And so, of course, in algebraic geometry, that would be some space of polynomial functions, whereas if we were doing, want to do differential geometry, it would be the C infinity functions on that manifold into the reals. Okay, now, basically, from the argument that I gave there, you can see that, first of all, I get my manifold back as a set of points by simply taking all the maps from that into the real numbers. And I can even, bring in infinitesimal arguments by putting in my dual numbers. All right. Now, you can furthermore show that that just giving me this algebra structure, I can recover the whole I recover the manifold. You say two different manifolds, they will have two different algebras. I can recover the manifold, its topology, and all that structure just from the algebra. And so, all right, and I don't go into details of that, I'll just mention that. And furthermore, if I have a mapping between two manifolds, let's say A to B, then that induces a mapping in the other direction of the functions on them. All right. And again, I can show that any homomorphism of algebras in these is going to correspond to a map of the manifolds. Basically, I can just proceed point by point and use the arguments I had before. All right, so that means that now I can phrase my thing all in terms of these algebras. And so now what I'm going to do is generalize my notion of space. Yes, sorry.
Just a pure curiosity. Mm-hmm. So given an isomorphic class of such maps,
yeah.
Do they differentiate the actual mappings up to diffeomorphism or up to?
Yeah, of course. This is categorical, so everything is up to isomorphism. Yes.
No, I mean it's categorically.
Yeah.
Isomorphism classes is like
sure.
the natural class we work
with,
right?
Yeah.
But then, given one isomorphism class of such mappings between C infinity ring structures, we know that this class corresponds to many possible mappings from A to B.
Yes, that's right.
And then for all those mappings correspond to the same isomorphic class. Do all those mappings, can we identify all those mappings up to diffeomorphism or up to homotopy?
Okay. Well, I mean, here we're just saying diffeomorphism. There's no algebraic topology of homotopy around here. I'm just doing, this is just plain, it's only diffeomorphism. There's no, I haven't done not doing any homotopy or anything like that. This is purely that. So the point is, I can then phrase all my operations in terms of working with the ring functions. So in particular, let me extend and say, well, now I'll put things in like the dual numbers. So for example, just to state the obvious, real numbers itself, well, that's of course, I can just think of as functions at one point. And then, so I can have dual numbers. So that gives me a new kind of space. And well, what is that space? Well, basically, by, from these arguments, I can see that I can think of this space, well, I have this as actually the space of all as a sort of well, okay, so let me just now introduce the word scheme. So scheme theory is basically in algebraic geometry just is when you say, okay, instead of talking about just varieties, I'm going to assume there's a space called a scheme, or an affine scheme more precisely, associated to any ring. So here I'm going to go from, just having manifolds to saying to any such, algebra, there is a geometry object called a scheme. So I'm going to say that corresponds to, so to R, I just have a single point, right? That's functions there. So here I'm going to call it, I'll just call it ordinary D, the space associated to that. And just to say the obvious also, of course, if we took smooth function on real line, that would have been, the real axis. So basically what happens, well, basically you can think of this as it's a sub-scheme of this. Why? Because, well, basically because we have a map going in the other direction here, the one we described before, where we evaluate the thing. And intuitively, this is basically going to be the sub-scheme that corresponds to all, to the infinitesimal elements of the real line. And now when we start talking this way is where Gersham's point becomes important. When we talk with the schemes, we have to be careful about our logic. So we don't confuse this scheme of real numbers with the classical real number axis.
So are those living in a topos?
They will.
The schemes?
Well, we'll put them in a topos later.
Okay.
For now, it's just a category of rings. We'll upgrade that to a topos in a minute. So, in fact, let's think so for now so let's think what category. So one, I could say, just a category of rings, I could do things like this. But actually, I want to have a nice, but if I'm going to do, to do things cleanly, let me be more selective which rings I want. So for example, if I was doing algebraic geometry, I probably wouldn't want all rings. I just want, nice polynomial rings or things like that. Not, for example, C infinity, which is also a ring. And so it turns out that, now I'll just go back over here, that a very nice class of rings to use is what's called a C infinity ring. So the idea is that, basically, let me just say what they are. Sorry. So, like I said, well, okay, so first I'll say what they are, then I can say what nice property they have. So, the idea is basically that, let's think. So first, most generally, we just have we have category of rings. Now, one way which I haven't mentioned explicitly, but implicitly I should have done, was say, well, I don't really want all rings here. If I'm doing things with real numbers, I only want ones that are algebras over the real numbers. And in particular, that's important when I talk about mappings between them, because if I just take either the real number as just a ring, I can have ring maps that do things like, funny things with things with irrationals. I could, ones that replace root 2 with minus root 2, etc., etc. But those wouldn't be interested, but I'm not interested in those, because among other things, if we're trying to do some form of analysis, none of those homomorphisms that do that are at all continuous, let alone smooth. So I would, so in order to exclude them, I would say, well, I also want the rings to be our algebra, so they have an action of the real numbers on them, and I want the morphisms to preserve that action. So I would have our algebra. So that means I have so it's, like I said, ring, but together with action of R by scalar multiplication. All right, but now, and if I was doing, let's say, real algebraic geometry, that would be just, I would have polynomial rings in there, and that's a perfectly good category to work with. However, if I wanted to do something like manifolds, where I have C infinity functions on them, you see in addition to, given a smooth function, in addition to multiplying by a scalar, I can do things like exponentiate that, and I'll get another smooth function. So if I have, f is smooth, well then so is exponential f, sine f, etc. So it's convenient to say I'm going to generalize to what I'm going to call C-star algebra, C-infinity algebra, or well, you call this ring. So saying not only do I have action by scalar multiplication, but for every smooth function I have an action on it. And how do the problem then of course is there's a lot of smooth functions, right? Scalar multiplication, that's a single operation with a scalar. Smooth function, well there's a lot of them, so how do I even define that consistently? There's a very slick way of doing it. And that way is the following. So I can write right here. Okay. The very slick definition. It's a. All right. So well, first I should say, let me just first define something that you probably will probably remember from Emilio's talk. So let me first define cart just to mean the category whose objects are the Rn's, and whose, for different values of n, and whose morphisms are the smooth maps between them. All right? Now, so I will say a C-infinity ring is just a functor from cart to set, which preserves products. All right, like I said, that's too slick, because obviously it doesn't look like a ring at all. You know, where's the addition? Where's the multiplication? Where's the unit? Where's the associative law? Well, it's actually, well, so we'd have to unpack it a little bit. So first of all, in this category, every object is the product of R with itself some number of times. So if a functor preserves products, that just means that on objects, well, that's just take n copies of that. All right? And then, all right, now what about morphisms? Well, in cart, a morphism is a smooth function. And in particular, because of it preserving products, I basically only need to worry about smooth functions that, only worry about smooth functions that go from just Rn to R, so set m equal to 1 for a moment. So let's just look at such a function. So what happens? Well, being a functor means I have, apply the functor to that, I get a morphism of these sets. So I have whatever my set f of R is, so I'm going to set from all right. It's a functor. I apply it. I get that. Now, let's think what that thing is. So basically, it means that for every smooth function, I have such an operation that so smooth function goes from R to n. Now I just get a thing from whatever this set f is to this set f for that. Now, furthermore, because all right, so in particular, I could obviously apply this. Well, there are certain smooth functions. One smooth function from R2 to R is just the addition function. There's another one, which is going to be the multiplication. So there's my ring operations. Now, to be a ring, however, they have to satisfy some identities, right? Associative law, distributive law, etc. All right, but how do we get those? Well, you see, you can write the, if you want to write down the associative law, basically those laws can be written in terms of composition and projection from Rn to R.
Is there classifying topos of C-infinity rings?
Oh, I don't know, a good question. I mean, probably, maybe, I don't know, maybe what's, oh boy, yes, I think that book might have an answer to, I don't know offhand, probably is one. And
these are the points of that topos.
Okay, I see. Yeah, right. I mean, it is some kind of a presheaf thing. So certainly, yeah, that's right. Well, I'm going to make another topos out of it in a minute. But But just to finish why it's a ring, so as I said, the ring axioms can be written in terms of, composition and projection. Since a functor is supposed to preserve products, it preserves projections. And the functor, it obviously preserves compositions, so these things will satisfy the ring axioms. But in addition to having an operations of the ring operations of adding and multiplying, I also have now, exponentiation, sines, and any other smooth function gives me an operation. And it's obviously all, and since it's defined this way, it clearly gives me all the coherence and consistency of them. Yeah, sorry.
One question. So, what is the difference between the C infinity ring we just defined and the C infinity of an M for some place?
Well, C infinity M is an instance of this.
Okay.
But there are other instances. For example, so for any manifold, yes, C infinity M will be a C infinity ring.
Yeah.
But these aren't the only ones. An important example is, for example, we take this ring of dual numbers. You see, that's also an instance of a C infinity ring. Why is that? Because when I act with a smooth function on a dual number, I just, I had the action that I wrote before, right? F of gives me f of x plus this. So it has an action of all smooth functions on it. So these dual numbers are also a C infinity ring. So you see, if I think about, say, okay, let's say if I say I'm now going to consider as my geometric space something like a scheme over this, I now get, in addition to what I would classically want, my manifolds, I'm also going to get things like this.
Can we view D itself as a manifold as well?
Well, I mean, a generalization of it, I guess it strictly isn't a manifold, right? It strictly isn't a manifold because, what would it be as one?
The space associated to boldface D is what we little d over there.
Right, we just made, that's right. It's not a manifold, it's some other kind of generalized space. I mean, intuitively you could say, it's an infinitesimal sub-neighborhood of a manifold, but of course, in the classical definition, you don't have that notion, really, so. So I would mention, so I guess okay, so then, yes, so I'll just say this, and initial times I skipped over, by the way, a part, well, okay, that's not so important. So anyhow, so that would be, so I get that. Now, furthermore, I'll just end up by saying, one level higher of generality, because you mentioned topos. So of course, there's a sense, so I could take, so basically, well, all right.
You said you were going to go from rings to totals.
Yes, that's what I'm about to do now.
Okay.
So what I'm saying is that, so let's say I have, I'll do that right here, and I'll probably end today's talk.
Hey, you never told us when's the next time you want to talk.
Oh, I don't know, we have to figure that out.
Okay.
Yes, we will figure out if I talk and when afterwards.
We called this part 1.
Right. Okay, so I'll make a part 2. But anyway, so just to finish the thing. So I have a category of C infinity rings. All right, I just told you what they are. And they include a category, and they, include smooth functions on manifolds, and they include other nice things like these infinitesimal rings. So hence I can do so that's a good category for doing my synthetic differential geometry. It also has nice properties like being closed under products. So I wrote that in my notes, which I'll publish soon, but basically, let's just say, if you remember in basic stories that in rings, if you remember, the product there winds up being basically tensor product of rings, and if you and it works it out and if you do in infinity rings, you find out you have a product and it behaves the way you want. For example, you'd want the ring associated to M cross A cross B to be the tensor product of ring for A and tensor B, and here it works out.
Has all limits and colimits.
Oh, yeah, sure. But the point is that particular one, of course, is what you'd want it to be. See, the point is if I took the category of rings and I took the product of A and B, I took smooth functions of that, the product in the category of our algebras would not be smooth functions on A and B. It would be a smaller thing. Whereas in infinity rings, it is exactly that. Yeah, sorry.
Tensor over, I guess, always C infinity R?
Well, here,
oh, no, just
no, but I just meant, all I meant is that, let's say if you're working, yeah, here I just meant, well, in this thing you have a, yeah, it would be a tensor over that, yes.
Excuse me,
Yeah.
I want to clarify, because like with schemes,
yes.
You always, really always specify a base scheme?
No, that's right.
And then you tensor over that base scheme.
That's right. So what I meant is,
what's the
well, you could use C infinity, I think, pretty sure it would be C infinity R.
Okay.
So my point was, if you took the base scheme, you took the tensor product over R, that would be too small.
Oh.
The reason is because you see, in tensor product you take always finite sums. So I would take, a finite sum of fi's times gi's, where the f sum space A and B. But the problem is, if they're polynomials, by taking a finite sum of polynomials, I'm going to get all polynomials on x and y. But on smooth functions, I only get some smooth functions that way. To get all smooth functions, I would have to, take something like an infinite product, which wouldn't quite work. Or at least I don't want to have to try to define the product, because that kind of defeats the whole idea here of not talking about analysis and just doing infinitesimals algebraically. But if I do C infinity rings, then you see if I took that tensor product, but then I need to get a C infinity to complete the thing by having all the real functions act on it. So that would then fix up that problem. That's what I meant. But now we want to make it, fix up more problems. So as we said, this thing will have, some sorts of limits, but all right, so, well, let me just get to the punchline. So the next thing we'll do is, as is usual in algebraic geometries, let's pass from using the category of rings to presheaves or sheaves over those rings. So we will consider, let's say, set, and this I'll just, so we can do that. Now, as usual, what does that bias? Well, this thing now is a topos. All right? And so that means, that gives us, and for a point of view of why we might want to use in differential geometry, well, one nice thing about topoi is that, well, in particular, they have, they're Cartesian closed categories, so they have exponential objects. So that means if I have a space A and a space B, I'm going to have that. Also, I'm going to have, and it's a topos. What makes a topos? Of course, that I have, sub-objects, or a space of sub-objects. So so what does this mean? So if I have two spaces A and B here, that means I have the space, loosely speaking, of mappings between them. So for example, if they were manifolds, this wouldn't be a manifold, it would be some infinite dimensional thing. Like, let's say, simplest case, R to the R. That would mean, well, that's the space of all smooth functions from R to R. That's that's infinite dimensional. But here, the nice thing, in this topos, I have that object. No functional analysis required. No figuring out how do I extend my definition of manifold to include infinite dimensional things like function spaces. The function spaces just automatically come out of a topos structure.
What is it, though?
Okay, what is it?
Yeah, like,
oh, you mean, well, I guess, okay, so obviously.
What is that? That's function space. It's not. So,
well, it's an object of this topos.
It's still, its dimension is still infinite, yeah?
Yes, that's right.
So what have we gained?
Well, what I've gained is I'm saying if I was doing, classical differential geometry.
Oh, I'd have to prove that.
How would you even define this space?
Okay.
And the problem, since it's, then you get the problem of, well, there are many ways of, for example, putting a topology on a function space. And then the problem is then you have to make a lot of ad hoc choices. But here, all that somehow gets taken care of under the rug by the topos theory.
That's pretty interesting.
It just automatically gives you some version of this, and I know I have mappings between them that behave,
Is it picking one of the topologies that we know?
Well, okay.
What do you mean by what is it?
Yeah, so there is a little bit of discussion that I remember from Colin McLarty, where he was saying how sometimes you get something like the Frechet topology out of this.
Oh, that's what it happens to be.
At least in some cases it's that or something. I remember I don't know the detail, but I know in Colin McClarty, he has a little chapter in his book on synthetic differential geometry, and he mentions that.
That's interesting, because then it suggests that like that's the correct topology quote.
Yeah, that's right, because in that it has very nice properties for the mappings. Now, of course, if you want a different topology, then you'd probably, you'd have to pick a different topos or a different construction for that one. Yes. Yeah.
Does this construction come with a topology with it at all?
Well, I guess you'd have to, well, it's okay, to find you'd have to think how you'd recover a topology. I mean, you could probably do some procedure, like I said, like first you recover the points, and then you try to do, well, it's the usual way you get a topology out of a ring, right? First we said we could get points as, homomorphisms into some target thing, say R. Or could have other types of points with whatever target. Now then I put a topology on that by saying, well, I want all the elements of this, all my functions, to be continuous. So you pick the weakest topology, and in algebraic geometry, that's how you get to the riskiest topology. Now, if we were dealing with topological spaces, that's how Gelfand and Naimark show, for example, that if I take the smooth bounded functions on a reasonably well-behaved topological space, I indeed recover that topology. So in fact, you could do that, and so not by Gelfand and Naimark's thing, I would be sure that if you took an ordinary manifold, yes, this would just give me back the usual topology on that manifold. If I just said I take the set of points as, the mappings from this ring into R, and make a topology by saying that all the functions that all the smooth functions it's a minimal topology, you need to make them all continuous, that would recover the ordinary topology in a manifold. So one could certainly say, take this topos, I don't know if the calculation's been done, but you could say, I have this object, consider all mappings from this to R, that gives me my points. I can easily figure what they are. Then I could say, well, given my class of mappings of this, what is the topology on here? That would make them smooth, and see what that is. Okay. Now, I remember, like I said, that Colin McClarty made some comments about Frechet topology, so I'm not sure if he's actually done the calculation or what, but that's the one thing that comes to mind. Okay. So that is at least a well-defined question.
I mean, if you look at, if by definition, this R to the R should just be the smooth, should just be C infinity R.
That's right.
Collection of all smooth functions. And I think that's...
Yeah, but then the point is there's many different ways of putting topologies on those things. Right. That's the, functional analysis, right? You see, given a function space like that, there are just many, many ways of putting topologies on them. I can put all different kind of norms and,
And I think the smallest topology that makes this evaluation functor continuous should just be what we call the L infinity topology.
It might very well be. Yeah. I just haven't seen that written as a file. I said we could start by looking at the McClarty reference, because at least he says something on that. And if he hasn't done it, we might need to finish the thing. But that is definitely definitely doable.
Right.
And okay, just to end off, I'll just say one last comment, and this will just be a few words. That now, as usual, when you do this is just usual presheaf topos. As you know, speaking of topology and topology related to things, as you know, oftentimes that doesn't work well because of covering issues. And in this case, if I just took set to C infinity ring, you would, for example, find out that here, I'd have trouble defining things like say if I took, let's say if I was just looking at C infinity of R, right? The real line. So I would want something like the usual properties of having my ordering on it and coverings to be sensibly behaved. So as often happens, well, in the presheaf topos that doesn't happen. So, but that can be fixed, and Dubuc showed a way of, showed particular study that, and he showed explicitly how to construct Grothendieck topology on this, such that, for example, if I take the real line here, it really does have now an ordering that behaves as the ordering should, and that covers of the real line behave properly too. I was just saying that just to complete the story. But yeah, But going back to this, but yeah, this is a good question. In fact, this, by the way, earlier I mentioned, so I'll just end up with the remark of how I got into this rabbit hole. It happened to be, it happened to be because I was, in the course of science doing that ultimately came from biology. I was trying to solve we got a partial differential equation. And I noticed you could solve that partial differential equation, as often is the case by using Lie groups. Now, the only problem was that for some instances of this equation, I got a nice, so for some of the simpler instances, I got a nice, basically a simple, the Lie group was just, ordinary Lie group was something like affine transforms of the plane. So nice fine measure. Now there was a more complicated instance of our model, which was still exactly solvable. And I was wondering, well, what is the group associated to that? And after about a year of work, I found one, but it was infinite dimensional. In fact, it was something like R to that finite dimensional Lie group. And so my question is, well, how the heck do I make sense of that? And that's what drove me to the, reminded me of that thing I read in synthetic differential geometry. And then when I read this, found that, oh, okay, and exactly the selling point for me was this fact that it automatically gave me such a thing without having to think of, all the different topologies I could have put on that and that, because when I looked, at, yes, people study such groups with functional analysis, but there's many choices to be made. And so I found it, so for me that was actually a practical use of it. Now it turned out I was able to write the paper without that, but that's what just wanted to say as a personal note, that's what led me to this. Yes, yeah, sorry.
I was just going to ask if you did manage to solve it.
Yes.
Okay, yeah.
No, I did solve it, yeah. And once my collaborators reappear, we will have the paper done.
Ray, you want to give an advertisement what you're going to do in part B?
Well, so what I was thinking of doing, one, I could say more about what I just said now. I want to say about groups, because maybe not that thing, but just even how to doing Lie groups in synthetic differential geometry. Because the basic idea of a Lie group is that we have a continuous group of transforms like rotations, and intuitively you want to imagine they're groups you like to think in terms of generators and relations. But for a continuous group, that would give you the idea of something like the generator you would want to be an infinitesimal. Well, this gives you a notion of infinitesimal that you can actually use to do that. And in fact, that was the thing I studied very well in Kock's book, so I was doing that. Plus, I wanted to also then take a few minutes more to say maybe some words about, like I said, perhaps about the non-standard analysis, and also about some other, also about what I'll call the the top-down approach. So the way I explained it here is what I'll call was sort of bottom-up. I started with simple, with just real functions, and I built up gradually up to different, gradually from that to things like the infinitesimals, then to C infinity rings, and finally up this topos. However, usually when the subject is discussed, people take a top-down approach where they start with axioms where we say, let's assume we have, a category, could be a topos, maybe not a topos, but that satisfies certain conditions, such as that analog of the Taylor's theorem or whatever. And then given these axioms, well, we can derive, some results. That's our differential geometry. And then we have the problem of, and then we can talk about models, which is saying how do I actually construct a category with those properties. So I would just want to, just for at least sake of completeness, say something about that. And also just a general, also get to this point, that came up today. Like when I mentioned the Taylor series remainder, as it was correctly pointed out, well, you didn't prove that here, you just assumed that. And that is actually a very important feature of synthetic differential geometry that unlike in non-standard analysis where I can actually prove classical theorems of analysis, here, since I'm doing things purely algebraic, I can't actually do things with infinite series or limits in them. So what I do instead is I just assume results from there as axioms and derive consequences from them. And so I just would want to say maybe a few words about that general outlook on how it uses technique. That it has this feature that, I would say that it is a way of using, that you don't prove unbalanced results, you just use, it's just a way of using them and thinking about them intuitively. So I'd like to say a few words on that. And so if you're all interested, we'll find a good date later this semester, and I will be back here.
Let's thank our speaker.
And I will also publish these notes that I've written once I've, edited them.
Nobody move.